So basically what happens as we change B? Okay, so what happens as we change B is, so as we change B, the vertex appears to trace out a parabolic path. Okay, so again, this relationship is not easily defined, so we can't calculate exactly where the vertex is going to be. But that B value, as you change it, clearly it's following a parabolic path. So there's some sort of relationship going on there. At this point, we don't really know what it is, but there is this relationship. Okay, so how can we match the general form graphs to these parabolas? Again, the two things that we're going to look at are the direction of opening and expansion factor and the y-intercept. Okay, so I can see that the y-intercept here is +4. So the only one that has a +4 y-intercept is here. Okay, this one is facing down, yeah, it has both criteria. So we're going to connect A with this one here. Okay, so that one goes with A. If we take a look at this one here, this one is opening up in a y-intercept of -1. The only one that has a y-intercept of -1 is this one here, so we're going to say that goes with B. And this one here is opening down, it's got a y-intercept that's negative, yeah, those both match. So we'll say that C goes with this one here. And based on just those two criteria, we can kind of start eliminating and get a sense of which graphs go with which. So that's the standard form. It doesn't tell us a lot about the graph, let's face it. It's the y-intercept is not a symmetrical point, okay, it's not the vertex. The A value does tell us which direction it's opening. The B value was really quite undefined, and although we know it has something to do with vertex, really it's not that straightforward. Okay, so we really want to relate it to the graphing form. Okay, this graphing form is really our go-to form. This P value is going to shift the parabola. This Q value also is going to shift. This one happens to shift it horizontally. This one shifts it vertically. So how is it that we can connect this form of the quadratic to this form of the quadratic? Well, what we can do is we can expand this out and we can try to make the parts equal to each other. We can match. This process is called equating coefficients, and this is a very useful strategy, not just in this case, but in general. If we have different terms of a polynomial, we can say that the quadratic coefficient must match the quadratic coefficient, the linear coefficient must match, and the constant terms must match. So as I expand out this parabola here, okay, I need to FOIL this out. Okay, when I square that, I'm going to end up with x squared minus xp plus q squared, plus p squared. Okay, and then the plus q on the outside. And then I can combine like terms and expand those brackets. So I end up with ax squared minus 2px. Yeah, so 2apx. I need to multiply by a. That's negative 2xp, and then we need to introduce the a in there, plus ap squared plus q. Okay, so let's see here. Let's combine so this is going to be an x in here. Okay, so we've combined our like terms. Okay, and this is what it looks like. Now, what we want to do then is we want to match the coefficient. So notice that there's an x squared. There's an x term, and this is a constant term, and that's a constant term. Now, what's really straightforward is that this a and this a match. Okay, they're the same. A is equal to a. Okay? And so we have A equal to A, so no problem. The B, on the other hand, is this coefficient here. And we can say that B must be equal to that same coefficient, so negative 2AP. And then the C term must be equivalent to this term here. That's AP squared plus Q. So those are all equivalent. So the A's, we just basically, corroborating that these A's are the same. We've already said that. Now what's happens is this middle term AP, we can say that the P, or the horizontal shift, must be connected to these two terms. Okay, so the A term and the B term. Okay, and which then the P definitely does affect the vertex, and it does get affected by that B. And then the constant term, which is the y-intercept, really just is affected by this mess here. We're not going to really get too much into that, but there it is, if we want to know what that is. Okay, so what do we do with this? Well, we can do something called Vieta's formula, and this is the key one right here. So I'm just going to circle. Really, we want the vertex, and this does not give us the vertex. However, the P does give us the vertex. So what we're going to do is we're going to solve for the P. And when we solve for P, we end up with this formula, negative B over 2A. So if we take a look at that, okay, I'll do it right here, right in front of you. If I want to solve for P, I divide both sides by negative 2A. Well, this then is something called Vieta's formula. If I want to find the x-coordinate of the vertex, I'm going to use this formula. And notice that when we changed B, the location of our vertex did change. And in fact, there it is. There's definitely some connection here to that. Now, it's not a simple connection because we have to worry about the A value and the height of the vertex too. But our B is involved in the vertex.